Suppose I have two systems, system A and system A prime. And we're going to let those systems interact with each other. As I said, the types of interactions we're going to talk about are thermal interactions and mechanical interactions. If I have a situation where I have these two systems, let's say they're in contact, and the external parameters remain fixed. The only way they can interact then is by exchanging heat with thermal energy back and forth. That's what we call a thermal interaction. In the case where maybe we have the same two systems, but we allow them to interact such that the external parameters are not fixed, but we don't allow heat to go back and forth, that's when we talk about a mechanical interaction. For example, one system can do work on the other. So in this case, what we can say is, let's define work. If work is being done by system A on system A prime, we say that the work done on A prime is plus W. The work done by system A is minus W. Okay. If we go back to the first situation, if system A gains some amount of heat, we call it plus Q, system A prime would lose some heat minus Q. And it all must be, no matter how they interact, the total energy is going to be, total energy change is going to be fixed because these two guys are isolated from the rest of the universe in each case. Now, examples of a mechanical interaction. Suppose we have the following situation. Suppose I have a flywheel inside a liquid, and I have it attached to a pulley system, like so. And that pulley system's attached to a weight. So here's my liquid. If I allow this weight to fall, the potential energy of that system will change by the weight. Suppose it falls some distance y. The potential energy change would be W times y. But that being the case, while the potential energy of this system would decrease by W1, that must mean that I'm giving energy in the form of rotational energy to this, this body inside the liquid, and will cause it to rotate. So what I've lost in potential energy outside is going to be exactly equal to what I gain in rotational energy inside. So that's a good example of a mechanical interaction. And there are plenty of others. Now, we can also talk about the fact that we can have two systems interacting with both mechanical and thermal interactions taking place. That being the case, I can write my total conservation of energy as Q minus W, where Q is any heat added to the system, W is work done by the system. We can show nice example of where we have two types of interactions. So let's, again, we have two systems, A and A prime, and let's let them be suppose I have two gases, two different gases in A and A prime. And I can conceive of four situations. So the first one, boring, no interaction. So in that case, nothing's happening. So maybe I have a piston in between these two compartments, and the piston is clamped. So there's no motion of the piston, so there's no mechanical interactions. And I have this thing thermally isolated so that there's no heat being transferred between each side. So that would be no interactions, and of course, that's boring. How about in the second case? We keep a piston clamped, so there's no mechanical interactions, but allow heat to be transferred between the two systems. So we remove the insulating part and we allow heat to be transferred. In that case, no work will be done, but any energy change will be equal to however much heat is gained by one system or lost by the other. In the third case, we have a movable piston. But the systems are thermally isolated from each other. So in this case, any change in internal energy would just be equal to minus the work done by one system on the other. And then in the fourth case, of course, we allow both motion of the piston